So this first page is a reference page, and I'm going to write that down. And what you want to do is use this first page as a reference when you're graphing things. So you reference these graphs for the shapes of common functions. And you'll see in this section, what we do is we start with the general shape of what a function looks like, and then we graph it by shifting it around based on the information in the following pages. And so what I want to just start by doing is sort of just going through each picture and pointing out like the pattern. Right, so first of all, linear functions are straight lines. We already knew that. The power function is the one I want to focus on first, which is that we have x squared that looks like a u, x cubed does that opposite thing, x to the fourth looks like a u again, x to the fifth does the opposite thing, and so in general, if we have x raised to an even power, it has a u shaped. Okay, so x to the 6th would look like this, x to the 8th would look like that, right? X to the 20th would look like that. And in general, x raised to the odd power, whoops, not xo, but x raised to the odd power is going to have the other kind of shape. And so that's what you should be taking away from this second row. X to the odd power looks like that. Okay? And we get a similar kind of thing in the next row. These are the root functions. And I know, in order to get this on one page, I had to kind of zoom out, and so the graphs are small. But you can look at your own paper if you want to get a closer look. But the root functions, you can see that the even roots look like this. They have this kind of shape. And the odd roots have this kind of shape. Very similar to the way these guys work. And so, the square root looks like this. Fourth root looks like this. Sixth root would also look like that. 10th root would look like that, etc. Okay? The reciprocal functions isn't one we see a lot, but you will see it a little bit, especially in the homework. And this is showing you the difference between 1 over x and 1 over x squared. And so in general, let me use some color this time. 1 over x to the odd power looks like this. And 1 over x to the even will look like the other one. Right, so in general, 1 over x to the odd looks like that, and 1 over x to the even looks like that. And so keep those in mind. As we keep going down the page here, you can go ahead and cross out the greatest integer function. This is just kind of a weird special case. The reason I put this one in is because we do want to know what the absolute value looks like. Absolute value is one we will see and we will graph. And so the difference between the absolute value function and the, say, even-powered functions up here is that these ones, the absolute values form a 90-degree angle. Okay, that's like a 90-degree angle there, where the other ones have a curved bottom. So if you're looking at a graph and you're wondering whether or not it's an even-powered, x raised to the even, or you're wondering whether or not it's absolute values have corners. And these ones have curved bottoms. Okay? And so what we're going to do on the pages to follow is we kind of start with one of these general shapes, and then depending on what the problem looks like, we move that shape around the xy axis. So you'll see what I mean, and you want to use this as a reference. I'm going to use this as a reference, and so it's just nice to have this one handy. As we go forward here, there's 3 things that I'm looking for when you graph something. Every graph needs the following things. So when I go and I graph or I grade a quiz or a test, I'm looking for these 3 things. Number 1, the correct shape. That's where this page comes in. Looking for the shape to be correct. I'm also looking for any stretches or shifts. You'll see what I mean when we start doing this. And the third thing that I'm looking for you to show on a graph is any intercepts. So any x and y intercepts. So keep that in mind when we're doing this, and I will do those 3 things when we go through. Now, this might be a good time to mention, the homework for this stuff is different than what tests and quizzes will look like, because the homework's online, you can't draw things on the computer, and so these homeworks oftentimes end up being multiple choice, where it gives you a graph and then asks you to write the equation, or maybe it gives you an equation and asks you to match it up with a graph, or it asks you to pick some drop-down menu or something. But generally, a lot of times they're multiple choice. Now, when you're doing the homework, you should be drawing the pictures, because on a test and a quiz, I'm going to want you to draw pictures like we'll do today. And so, I think the reason people often end up not doing well in this material is because you don't practice it the way I'm telling you to do it right now. When you see a problem in the homework, you should draw a picture and then match your picture up to the picture on the page. If you're just looking at the picture and then you're like matching multiple choice style and, just so you can get the right answer, that's not helping you. It helps you get like 0.00% of a grade point on your final average, but it's digging yourself into a hole on a test. So I can't stress that enough. Please draw some pictures in your notes when you're doing this stuff. Lots and lots of pictures. Questions before we look at how we do some of this? Thoughts about any of these pictures or anything? Okay. So let's look at the first page. The first page of this transformations section is all about shifting vertically and horizontally. And what I'm going to do as we go through this is I'm going to explain the concept, but I'd like to sort of also try to explain the intuition behind the concept so you don't have to memorize things, right? Remember we talked about that. If you just kind of understand why things are true, then you don't have to memorize them. They just make sense, right? So the first thing is vertical shift. This is the one that's usually the easiest to learn, so that's why it's first. And so what we have here in our pictures and what this box is showing us is that if we have C, which is some positive number, if we add C on the outside of a function, so we take a function and we add C to it, it moves that function up by C. And if we subtract C from the function, it moves the function down C. And that's what's being shown in this picture. If this is our original function, the bottom one, the blue one, then adding C on the outside shifts that thing up by C. And if we take our function, which is blue, and we shift it down, and we subtract C, it shifts it down that many. So for example, let me do a quick, and in these following examples, I am going to draw two pictures. I'm going to draw the original in dotted red, and I'm going to draw the transformation in solid blue. I guess it's the opposite of what these are. Maybe I should have switched that. Too late now. Okay. So let's do x squared. So x squared we know looks like this, and I know that because I've memorized that front page. All right. If you don't believe me, x squared looks like a u, right? Looks like a u. If we add a number on the outside of it, like x squared plus 5, it just takes this graph and it moves it up, however many units we add to it. So x squared plus 5 might look like this. The exact same graph, or at least I tried to draw the same graph, but it moved up 5, and so the new intercept is up here at 5. Right? It used to be down here at 0, and now it's up here at 5 because we added 5 to it. And think about why that's true. X squared are the y values. When we plug an x into x squared, a y value comes out, right? And so if we add 5 to x squared, it's like we're adding 5 to every single y value. And so if you add 5 to every y value, it just shifts the entire thing up 5, right? And similarly, if we subtracted 5, it would do the opposite. So let me draw x squared minus, use a different number. Let me do x squared minus 6 or something. Right, this is what x squared minus 6 might look like, where the new intercept is down at negative 6. Again, we just took every y value and we took 6 away from it, which is just going to move the whole thing down 6. And so going back to the things I'm looking for, right, we've got the correct shape, we've got the shift up or down, and I wrote the new intercept. And so I've got those three things that I'm looking for. Questions about this idea? Right, so this one's, like I said, this one's the most straightforward one. If you just add a number outside of it, it moves it up or down, depending on whether it's positive or negative. Okay, let's look at the next one. Is everyone set with this one? So that's a vertical shift, right? This is a vertical shift. The next one is talking about horizontal shifts. So a horizontal shift is left and right, obviously, right? And so again, let's pretend c is a positive number. If we plug x minus c into a function, that will move the graph to the right c. And if we plug in x plus c into a function, that moves that function to the left. So there's two things I want to point out about this. First of all, this is like a composite thing, right? This is from test 1. This is a composite function where you're plugging one function into another. This is just like that x plus h problem from the test that I just handed back. That's one thing I want to point out. The other thing I want to point out is it's kind of counterintuitive, this one. You know, usually when we associate negative with moving to the left, I would think. That's how I associate it. But when you plug in a negative x or a negative c, it moves it to the right, actually. And a plus moves it to the left. And so it's kind of counterintuitive the way those things work. So keep that in mind. But, well, yeah. And so this is what it looks like pictorially. If this is our function, f of x, then if we plug in a negative c, it just moved that thing to the right c. And if we have f of x as the blue, and we plug in an x plus c, it moved it to the left. So let's look at one, let's look at an example. Question? Yeah?
C is just a variable to represent a number that is plugged in.
It's some number, yeah. So we'll see, so for example, let me show you one and then you can let me know if it makes sense. So c is just a number, so let's pretend we had x cubed. So this is what normal x cubed looks like. And so if I plug in an x plus or minus some other number, it's going to shift that left or right. And so for example, this graph has been shifted to the right, and this might be x minus 3 cubed. See how that's in the x minus 3 is inside of the x cubed, which is what makes it a shift to a horizontal shift rather than a vertical. Right? On the previous one, the plus 5 was added outside of the x squared, right? The plus 5 is not being squared in the first one. But in the second one, the x minus 3 is entirely inside of the x cubed, which is what shifts it to the right. Yes?
I was just going to say, so in the situation where you got rid of the parentheses, it would look like that, but it would be shifting.
If the minus 3 was not inside there?
So if it wasn't in parentheses, it was just x minus 3 cubed, then in that case it would look like that, but it would be shifting down.
If it was x cubed minus 3. If it was x cubed minus 3, it would be shifting it down. But if it's x minus 3, parentheses, cubed, it's moving it to the right. And to give you some intuition about why that works and why it's kind of counterintuitive, when we plug a number in for x, like we plug in 0, for example, it actually plots the value at negative 3 instead of at 0. And so when we plug in 0 into this function, it actually reaches over and it grabs the value at negative 3 and plots that instead. And so that's why it plots this one at 0 instead of this one. And so this one gets plotted, which it moved over. See that? When you plug in a value, it actually plugs in 3 less than that value, which is 3 to the left, and so it pulls it over to the right. Let's write down the intercepts. So I'm going to start with the y-intercept. Does anyone remember how we do intercepts? We learned this in the line section. Remember, Tom?
Plug in 0 for x and whatever you get is your y-intercept.
Yeah, good. So for the y-intercept, you plug in x equals 0 and see what happens. So you have y equals 0 minus 3 cubed, which is minus 27. And so this new intercept down here is going to be at minus 27. So we have that new intercept. And so then the opposite, we do the opposite for the x-intercept, right? If you want to know the x-intercept, you plug in y equals 0. And so if we plug in y equals 0, we get 0 equals x minus 3 cubed. And so that means x minus 3 has to be 0. And so that means x is 3. And so this new x-intercept is 3. So I've got my shape correctly, I have shifted it correctly, and I have my intercepts. So those 3 things. Questions?
Would you be able to, like, just get rid of the cube
I'm sorry?
on the very end?
Oh, on this one?
Yeah.
I took a cube root. I did like a cube root right there. Yeah, so to solve that equation, we take a cube root to get rid of the cube, and we get what's inside there. The other way to think about that is, if we want to cube something and it end up being 0, then whatever we're cubing needs to be 0. You can't cube a not 0 number and get 0. And so that means x minus 3 has to be 0. That's the other way to kind of think about that. And the other thing I want to point out is, do we really need to do that at all? Why not, Nick? I know you know it, so just be a little more explanatory.
I'm actually not sure why.
Oh, I think you know.
Oh, no, I forget.
Yeah, I know you knew it. It was right there. You were like real positive about it. Rachel?
Because it's the C value.
Yeah.
And whether it's negative or positive determines how far it shifts or which way and how far.
Exactly. Right. So the intercept used to be at 0, 0, and we shifted the graph to the right 3, and so it moved over to 3. Right. So this x minus 3 is, since it's a horizontal shift, it just shifted the x-intercept horizontally. Right. For the same reason that we didn't need to do these up here. We could have solved for those intercepts, but I just knew that it moved from 0 and it moved down 6, and so we didn't really need to do the algebra there. I just wanted to show you this one just to be clear about how we need to do that in problems where it's not as straightforward. Like on the next one, for example, we won't be able to just do that one. So let's look at the next one. So I want to do an example that uses both of these things. So let's graph the following. F of x equals absolute value of x plus 5 minus 2. So this first page, this reference page of all these graphs is important, right? Because we need to know the shape that we're moving around. We start with one of these shapes, and then we shift it around up and down, left and right. We'll flip it, we'll stretch it, etc. So what graph or what base function are we using? What are we going to shift around? Yeah, absolute value, right? We've got the absolute value in this problem, and so this is a transformation of this graph. It's an absolute value graph. And so that's the first thing I want to write down, is that we are going to transform absolute value. And so that's important too, because then we need to compare this function to the absolute value. What's the difference between what's written down here and the absolute value of x? For one thing, there's a 2 subtracted from it, but what else? Andrew?
There's the plus 5.
And there's a plus 5 inside of it. And so maybe Andrew can tell me, what's that plus 5 doing?
It's moving into the...
Yes, this is shifting absolute value to the left 5. Because we have an x plus 5, and it's inside the absolute value. This is like if f of x was absolute value of x, f of x plus 5 would be absolute value of x plus 5. So this is a left shift, again, because it's inside the absolute value. Because the minus 2 is outside of it, that's what's moving it down. And so this is going to shift absolute value down 2. So I know absolute value looks like a V, so I'm going to write that down first. It's got that corner. That's what absolute value of x looks like. And so we're going to move this thing to the left 5 and down 2. And so I already know like where this vertex is, right? You call the corner there, that corner spot is called the vertex. And so instead of being at 0, 0, where is it going to be? It's going to be at -5, -2, right? Because we move left 5 and down 2. And so it's going to be over here at -5, -2. Oops, let me use a different color. Sorry about that. And I know it's going to be a V. It's going to be the same shape. So it's going to look like that and like that. All right, so this is the point -5, -2. Questions about that part so far? So let me just mention why I care about this. This might seem like not, why do we care? We have graphing calculators and stuff. Because first of all, when you use a graphing calculator, you want to be able to catch your errors, right? Especially if it's a more complicated function. And so knowing the shape of what it looks like and kind of having an idea what it looks like is actually really important to catching simple mistakes. And you also kind of want to know what a function looks like before you do anything with it. It helps to know that this starts at -5, -2, and everything is above that point. Like that might have some meaning for your function. And so having an intuition about what the function looks like can be really, really helpful and important sometimes. And so in other words, we don't use this method to draw really nice pictures. We use this method to kind of have an idea of what the function looks like before we do anything with it. That's the important part of this. And so I'm not looking for nice drawings, right? I won't draw a single nice drawing. I don't know how. And I'm not expecting you to. I just want to see those three things: the right shape, shifts, intercepts. Okay, so let's do the intercepts. And this isn't an obvious one. I don't know what those intercepts are because it's kind of confusing, right? So let's solve for them. So the x-intercept, you let y equal 0 and solve for x. And on the x-intercept, you let, for the y-intercept, you let y equal 0 and you solve for y. Oops, I forgot to write y-intercept. And so when I let y equal 0, I'll do that one first. You have x plus 5, absolute value, minus 2 equals 0. This is a question from the first test. Right, this is how do we solve an absolute value equation. This is why we talk about doing that. You add the 2 to the other side. And now we have this form. A lot of people struggled on this question, so this is maybe a good review. Now we write down x plus 5 equals the positive 2, or x plus 5 equals negative 2. And we solve both of those. And so we're going to get 2 answers. And that makes sense because if we look at our graph, it looks like we should get 2 answers. There's 2 x-intercepts. And so I usually like to draw the picture before I draw the intercepts because it helps guide me solving the intercepts. Like I already know that I'm looking for 2 negative intercepts. That's x-intercepts. And so hopefully I get 2 negative things out of this, right? And it looks like I will. So I get x equals negative 3 or x equals negative 7. And so that's good because it looks like I should get 2 negative intercepts, and I did. Right, so that's helpful. Helpful to draw it first, I think. And then on the y-intercept, if we let x equal 0, we just get y equals 0 plus 5 minus 2. And so that's going to be positive 3. And so this is a positive 3 right there. And again, that's good because it looks like it should be positive, not too far off the x-axis, so 3 sounds about right. All right, so in other words, matching your sort of visual interpretation of what the shifts are with your algebra is a good final check to make sure you did things right. In other words, if I got some positive number for an x-intercept and I looked at my graph, I should know that something's not right. Either my graph isn't right or my intercept wasn't right, one or the other. But it matches up, so it's good. Questions about this idea? This page at all? Yeah.
So every time we are about to draw the graph here, what would you like advise us to do? Do you want us to kind of intercept first, to copy the intercept first?
I think it makes sense to draw the shift first because you're going to know what the shifts are, like left, right, up, down, flip, whatever it happens to be. So I would recommend sketching the graph and then thinking about what the intercepts are secondary. That's in my opinion the best way to do it. But you can play around with them and try it yourself and see you may like it differently. I don't know. Other questions? All right, let's look at reflecting. So when we reflect graphs, we're talking about flipping them over, and either flipping them upside down or flipping them side to side. And I had a really great question in my morning class today, which was, if there's more than one thing to do, like on that last question, there was more than one shift, we shifted left and then down. Does it matter whether you shift down and then left or left and then down? Not in shifts, but in reflections it does matter. And so I just want to make a quick note here. This is the only time it matters with this stuff. You usually want to reflect before doing other transformations. Just keep that in mind. Whoops, transformations, if I can spell quick. I swear, whenever I'm starting to do a video, I can't write or spell. So just keep that in mind, and you can think about that. If you flip something upside down and then shift it left, it's different than shifting it left and then flipping it upside down. And so we want to reflect before we do those things. Keep that in mind. There's only a couple times that'll be an issue, but keep that in mind. Okay, so here's how these two things work. So we've got our function f of x. If we multiply the function by -1, it reflects that function about the x-axis. And so that's what's being shown in the left graph here. If we have f of x and multiply it by -1, it takes this function and it flips it upside down like this. So this like this, right, over the x-axis. And you can see that's what's happening between those two graphs. And notice that the negative sign's outside the function. If we multiply the x inside the function by -1, that reflects the graph around the y-axis. And so that's like starting with this one and flipping it over to this one, around the y, like this, right? And let's think about why that is. Again, f of x kind of represents y values, right? It's all the y values. And so if we multiply all the y values by -1, it takes the positive ones and makes them negative, and it makes the negative ones and makes them positive. And so that's what gives you this kind of flipping action, because it just literally flips, makes them opposite, right? And so I'm going to write that down. I really think it's super helpful to just understand that rather than memorizing it. And so minus f of x, it takes all the y values and multiplies them by -1. And in doing so, that flips the graph upside down. So I refer to that as upside down, like over the x-axis, upside down. Similarly, if we multiply all the x values by -1, that's what's going on with this f of minus x. It makes all the negative x values positive and the positive x values negative. And so it does the opposite where we're doing this kind of flipping instead, because we're flipping over with the x values, right? And so let me write that down. So 2. F of minus x, when there's a minus x inside the function, that takes each potential x value and instead uses the minus x value. Right? So if you plug in a 2, it's actually going to plug in a -2. And if you plug in a positive 10, it actually plugs in a -10. So it does the opposite sort of flipping where it flips it from side to side. And so thus, it flips the graph horizontally. And I'll just try to use the more precise term. Upside down is really vertically. Try to be more precise about that. Questions about that concept? Before we look at a couple of them. So what about this one? Let's look at square root. So I'm going to draw the square root of x. I know square root looks like this. If it's an even function, right, it kind of like slowly increases and then it starts to flatten out. And so that looks like this. That's what square root looks like, square root of x. And so minus square root of x would do that same thing, but we'd flip it upside down. Oh gosh, I just did it again. Vertically. Because we flipped it over the y-axis, or the x-axis, excuse me. All right, we just took every y value and we made all the positive ones negative. And so it flips over like that.
Is this different than graphing quadratics or polynomials?
This is different than graphing polynomials, yes.
How's-
We're going to
I
do
know
that
that's
too.
different, but like how's that?
Because polynomials, so this is different than graphing polynomials because every polynomial, when you have a different degree, doesn't fit any of these forms. Like, it's not like we're just adding a number on the outside. We're like adding an x squared or something like that. And so that's a completely different kind of thing. And to do that, what we do is we find zeros and we test points in between the zeros. We're going to do that literally in the next section, I think. So we'll see that. Yeah, go ahead though. You have a follow-up?
Yes, that's when like we find the vertex and everything.
I'm not sure what you're referring to on that. That might be that might be this. Anyway, we'll see that though. Let me just draw one more. We've got 1 minute left. I want to draw one more picture to drive this home. So let's do absolute value, or square root one more time. And I'm going to do both of them. So let's do square root of minus x. So that's going to be this. See how the minus sign is inside the square root compared to outside? Why is it? That looks weird though, doesn't it? It almost looks like we're plugging in a negative number into square root. Why is that? Why is that okay? Yeah, because we're plugging in negative numbers. So when we plug negative numbers into x, they become positive by that negative sign. So that's why it's over this way. But anyway, intuitively from this, we flipped it like that because we plugged a negative x inside. Let me do both real quick. How about this one? What equation would this one be? So I just took that last one and I flipped it vertically.
Negative square root of negative x.
Yeah, it's both of them. Right, we flipped it both ways. And so you could think of flipping it sideways and then vertically, or you could flip it vertically and then sideways, and you'd get to that graph both ways. So let's look at another one with, we'll combine another one with a couple. And let's stick with absolute, or a square root on this one again. So let's start again with square root of x. And let's think about let's do something from the last page and this page. So what is the minus square root of x plus 4? Obviously we're in a square root situation, right? We're starting with the square root, but we have a negative 1 on the outside of the square root and a plus 4 on the inside of the square root. And so just looking at this page, right, this negative 1 on the outside flips it vertically. So that's going to flip square root of x vertically around the x-axis. And so that's something on this page. So we know that whatever this looks like, it's going to be an upside down version of what I drew here. What's the plus 4 do? That's something from the last page. So that's a plus 4, an x plus 4 inside of the square root, right? Does anyone have an idea what that does? It's a shift. It's some sort of shift, you know?
It moves it up.
So if the plus 4 was outside the square root, it would move it up. And so instead of up, what's the other one? Yeah, to the left. Because it's inside the square root. That's an important distinction. If that plus 4 was outside of the square root, it would move it up. But because it's inside, it's going to shift square root to the left 4. And remember, this is that one that's a little counterintuitive. Usually, I don't know, when I usually see something that says plus 4, to me, I want to move it to the right, because plus means to the right. But so just remember that it's the opposite in some sense of what you might think. And so what we're doing is we're taking the square root and we're going to flip it upside down because of the negative, and then we move it to the left because of the shift. Is that okay? And so it's going to be an upside down version of that. So just, think with me what it's going to look like. You flip it upside down, and so it's now it's down here, but then we're going to move it to the left as well, and so it's going to be over here going down like that. So that's what minus square root of x plus 4 might look like. Questions? And so I wrote this down on the first page last time, but I'll just remind you, the three things I'm looking for are the correct shape, right? Any shifts that take place, and then any intercepts that exist. And so we've got two of those, right? We've got the shape, it looks like a square root shape. We did the shift, we flipped it and we shifted it, so that's good. And now we just need to figure out what the intercepts are. And so I'll remind you, when we figure out what the x-intercept is, you set y equal to 0, right? And so we do minus square root of x plus 4 equals 0. That's how we figure out what the x-intercept is. And we can solve that for x. And so we can square both sides, and we'll get x plus 4 has to be 0. And so that means x equals minus 4. So that point right there is at minus 4, 0. And note that we didn't really need to do the algebra to get that. I want to always just remind you that's how we can get an intercept without thinking about it, or without conceptually thinking about it. But we could have gotten that without doing any of this algebra, right? Because we flipped this. It used to be at 0, 0. The x-intercept used to be at 0. But when we flipped it upside down, right, when we did the flip, it's still at 0. It would have been right here going down. And then we move it to the left 4. And so this minus 4 is because we moved it to the left 4. Right? So we really didn't need to do this one so much. But for the y-intercept, I don't know how to think about that one. We can't really get an easy way to think about where that is. And so we really do need to do some algebra for that. So for the y-intercept, you set x equal to 0. And so you get y equals minus square root of 0 plus 4. And so that's going to give us minus 2. Oops, sorry about that. Off the page there. And so it's a negative number, and so I usually like to draw the picture first because it makes me feel good that that's a negative number, right? Because it looks like it should be a negative number, it should be negative 2, that looks like it's good. So that's a negative 2 right there. All right, and those are the three ingredients that we're looking for. Questions at all? So just kind of as a reminder, and if you page through the next couple pages, you'll see this, but we're going to add a little more complexity every time, right? We started with shifting left and right, up and down. We're now flipping things, and then on the next 2 pages, we're going to be stretching and shrinking. And so I'm just saying that because if anything's a little unclear, we're just going to add kind of more complexity every page. And so this is really a great time to ask questions, even though it's 8 o'clock in the morning and you might be a little bit tired. If you're a little confused about anything, by all means, shout it out there. That'll help you wake up, too. Thoughts? Yeah.
So why would the graph be shifting like up and down? Would that be different?
Yeah, so I know you weren't here last class, but if you turn to the previous page, adding and subtracting numbers inside and outside is what moves it up and down. And so inside is what moved it left and right, because the plus 4 is on the inside of the function. If it's on the outside, we move it up and down. And so let's look at one like that right now, too. And if you haven't downloaded those notes from last class, you should take a look at those. Let's look at a cube root function. So let's start with the cube root. I'm looking at this page. I want to do a cube root thing. And so cube root, remember, looks like this. So it looks like the square root, right? Like if we covered up the bottom half, it looks just like the square root, except we also have this bottom half, because you can plug negative numbers into cube roots. So let's start with the cube root, and let's shift that one. So it starts like this, does this kind of thing. That's what the cube root looks like. And so let's draw a transformation of that, and let's do the cube root of minus x minus 1. And so just looking back on the last problem and that last question that you just asked, notice the difference between this one, how the plus 4 is inside of the root, but on this one, the minus 1 is outside of the root. And so that's the difference between moving up and down and left and right. So in the last one, because the plus 4 was inside, we shifted to the left. But now because the plus 1 is outside of the root, that shifts it up or down. And because it's a minus, it moves it down, right? So this minus 1 is now going to shift the cube root down 1. And so we're going to start by thinking about shifting it maybe down, right? I forget what I was going to add to that. Does everyone see the difference between those two things? That's the one that usually ends up confusing people. Oh, I remember what I was going to say. Remember, because if we just subtract 1 from a function, it's like we take every y value and we subtract 1 from it. So that's what's taking it down. But when it's inside the radical, we're taking or adding or subtracting values from the x's, and so that's what shifts it left to right. It's the difference between adding or subtracting to the x's or adding subtracting to the y's. Okay, so the minus 1 shifts it down. That's from the last page, right? From the previous page from last time. What's the minus 1 do? That's inside the cube root. That's from this page, right? So what do you do if there's a minus 1 that's multiplying the x inside of the function? Okay? Yeah, that's what this property is right here, right? See how the x is being negated inside of the function? So that's this situation where the x is inside there. And so this is going to flip the cube root horizontally instead of vertically. Again, just compare it to the last one, right? This negative sign on the previous one was outside the root. That's what flipped it vertically. This one is inside the root, which is what flips it horizontally, right? Notice the difference there. And so we're thinking about taking this original and we're going to flip it horizontally, right, and shift it down 1. And so I will do my best impression of that, making it a little bit lower. You can already kind of imagine what it would look like, but it's going to look something like this. Right, you can see I tried to make it a little bit lower than this one because it moved down 1. It also shifted, it flipped horizontally, and so it's going the other way. And because it shifted down 1, we ended up getting a couple more intercepts too. Questions about the picture first? Because the picture is usually an important first step. And then you think about the intercepts, because now when I have a nice picture, I'm looking at this and I think, okay, I need some negative x-intercept and some negative y-intercept. And that's very helpful to kind of just know that. But you kind of need to be able to draw the picture before you get that information. So are there questions about that? All right, so let's do the x-intercept. So the x-intercept, you plug in y equals 0. So you do 0 equals cube root of minus x minus 1. If we're going to solve that equation for x, we want to isolate x, right? So we're going to add the 1 to the other side and get that. We want to get, sorry, that's a minus x in there. We want to get rid of the cube root, and so we cube everything, right? We cube everything on both sides, and then we get 1 equals minus x. And so that means that x equals minus 1. So that's good because it's a negative number and it looked like it should be negative. And so it fits our picture very well. And so that's an easy way to get the x-intercept. And then the y-intercept, it's usually a little bit easier because you just plug in x equals 0, right? So cube root of minus 0 minus 1. And so you just get y equals minus 1 as well. And so the two intercepts are at minus 1s, which is just a coincidence, right? They usually won't be the same. It just kind of worked out that way. Questions at all? So just to summarize here, what we've done so far in those first 2 pages is we've shifted things up and down, left and right. That was page 1. We've flipped things horizontally and vertically. That was this page. And now we're going to stretch things and shrink things vertically and horizontally. That's what's on the next 2 pages. And quite frankly, those are the more complicated ones. Those are the in my opinion, the harder ones to sort of visualize, and they can be a little tricky to draw sometimes. But anyway, we'll move on. Are there questions about this page? Is everyone all set with this page? Very good. All right. So this is the vertical stretching and shrinking page. Just to kind of foreshadow the next page, right? This is vertical stretching and shrinking, and the next page will be horizontal stretching and shrinking. And so they kind of do similar things, and they can produce similar looking pictures. And so there's a couple subtle differences that we want to make sure that we understand here. Okay. So there's two things going on here. Sort of like number 1 and number 2, right? You got two rows here. And you can see what we're doing in both these situations is we're multiplying the function by a number. So you can see we have c f of x. So we're taking our original function and we're multiplying it times some number. If that number you're multiplying by is bigger than 1, right? It's like you're taking all the y values and you're multiplying it by something bigger than 1. And so that's going to move up or down every y value. It's going to stretch it vertically. So if the number you multiply by is bigger than 1, it stretches the graph vertically by a factor of c. And if the number that you're multiplying by is between 0 and 1, it shrinks it. And so that's what's being shown in this graph right here. See how we have c greater than 1 and c between 0 and 1? In both these two graphs, our original function is the blue line. And you can see in this one, the blue line gets higher. We stretched it this way in this particular one. And the opposite happens in this one, right? The blue line in this one got shorter. That's because we compressed it, because what we multiplied by was less than 1. Right? Again, just look at the way this looks. C f of x. F of x are all the y values. So you're multiplying all the y values by some number. If that number is bigger than 1, it's going to make them all bigger or more negative, and that's how you get that stretchy action. If that number is less than 1, then it just brings all them down closer to the x-axis, and that's how you get the shrinking. So for example, and again, this one can be kind of hard to draw sometimes. Let me just show you what I mean. So for example, let's say we started with x to the 4th. So x to the 4th looks like x squared, right? It does that u kind of shape thing. Again, I'm referencing my first page here, and I just know that's what x to the 4th looks like. If we multiply x to the 4th by a number bigger than 1, like say 2, it takes all those values and it stretches them up by 2. And so 2x to the 4th would look like a stretchier version of x to the 4th. Right, so this is what 2x to the 4th might look like. We just took all the values and multiplied them by 2. And so it increases faster. And notice how all the blue line is inside of the red line, right? It's because we moved up the red line by a factor of 2 on each step. But if we multiplied that function by a number less than 1, like a third, for example, it would take all the red line, all the red dotted lines, and move them down by 1/3. And so that's going to be a shrinking kind of look, right? And so that might look like more like this. It's going to be kind of wider and less steep. So that might be 1/3 x to the 4th. So if we multiply by a number bigger than 1, stretches it. If we multiply by a number less than 1, it shrinks it. Yes?
So, shrinking, does it mean like basically looking at the slope? Because it seems so easy.
So the question is, does stretching and shrinking, is that looking at the slope?
Picture-wise.
Certainly most of the time. I'm trying to think if it's all the time or not. Yeah, in some sense. I mean, first of all, we usually only talk about slope with a straight line, right? But if you want to think of slope as how quickly the function is increasing, then yes. If we multiply it by a number bigger than 1, it's going to make the slope increase. Yeah, it's going to make the function increase quicker. And if we multiply by a number less than 1, it's going to make the function increase slower. And so, yeah, it'll decrease the slope or increase it. Yep, that's one way to think about it, yeah. And let's look at another one. Let's look at a perfect example of that again. Are there other questions about this before we look at one? So I'm going to do another comparison here. Let's do 4th root of x. I'm going to do the 4th root, and remember the 4th root, since it's an even root, it looks just like the square root. The only difference is it just increases a little bit slower. See how this one's a little bit steeper than that one is? But when we're just doing a sketch, for all intents and purposes, they look the same, right? So if we're just sketching a 4th root, it looks very similar to the square root. So a 4th root looks like this. Let's multiply that by a number bigger than 1 and less than 1. So if we multiply it by 10, for example, it takes every one of those points and moves it up by a factor of 10. And so it's just like a steeper, higher sloped version, right? So it might look like this instead. That might be what 10 4th root looks like. And if we multiply by something less than 1, like a 5th or something, it's just going to move all those points down by 1/5, which is going to make it look more flat. So that might be 1/5 4th root of x. And you can see I'm not fussing with any intercepts on these because the intercepts aren't changing on any of them so far. The intercepts were at 0, 0, and they've stayed at 0, 0 because we didn't shift them at all left or right, so the intercept stayed the same. And so that's kind of an important, interesting thing, which is that if we stretch or shrink something vertically, it may not change some of the intercepts. We'll see one in a second where it might, but just note that it may not. It's not going to change the x-intercepts, that for sure. It might change the y-intercepts. Let's look at another kind of sort of simple one. Let's look at the 5th root. So the 5th root looks, oh sorry, I got it.
For that one, like the first one that we did.
Yep.
How come that one moved the y? Or are they all starting from 0?
This one, yeah, they should all be at 0. I'm trying to not overlap them too much, but they should all be right at 0, 0. Yeah. So it doesn't change the y-intercept because we're multiplying the y values by a number, and since we're multiplying 0 by a number, they all stay 0 on that particular one.
If we're going to like, combine a bunch of the transformations together,
Yeah.
but I remember in school learning an equation that had like the order in which the transformations occurred on one, and I don't know if you know it, you could share it.
So we are going to be combining transformations. I'm not familiar with what equation you're talking about.
It's like negative a times x plus y, so it just shows, it's the full equation, and then it just has all of the, it's like the order of the transformations. So like you would do the vertical stretching first, and the horizontal stretching, and then I can probably email my old teacher.
Yeah, I can try to look for something like that. I'm not super familiar with that. What I did write down last time, which if you missed this last time, what I did mention was one thing is usually it doesn't matter so much the order of which you do these transformations, but sometimes it does, which is what you're pointing out. And what I found generally is that, and I wrote this down on the last page, you usually want to do any reflecting before you do any shifting. Because if you shift something and then reflect it, that's different than reflecting it and then shifting it. And so as, you know, the problems that I've seen in the homework and the ones that I usually assign and things, it expects you to reflect before doing any shifting. And so we're not going to spend like a ton of time on this. We're kind of just going to get the idea in this homework set, and then we're going to use this concept on other functions. We want to use this concept on logarithms, exponentials, and trig functions. That's really kind of what we're laying the groundwork for. And so it's possible maybe you went into it in more depth with non-exponential or trig functions in high school, more so than we are now. I'm not sure, but I can look into that and see if there's something specific. But I will just point out, at the very least, if there's a reflection, you should think about doing that first. Yeah. And I'll try to look up and see what you're talking about there. Other questions before we look at another one of these? I wanted to do x to the fifth because it's got negative and positive parts to it. And so when we when we stretch it vertically, it's maybe not, I don't know, you can see some interesting things happen. So if we have x to the fifth, which again, it looks just like x cubed, right? Except it increases steeper, and since we're just sketching things, like it looks exactly the same, essentially. If we multiply this number, or this function, by something bigger than 1, so let's do like 5x to the fifth, it stretches everything out vertically. And so obviously, maybe the obvious piece is this first part, right? This first part is going to look steeper like this. That might be like 5x to the fifth, because it got steeper, right? But the negative version also got steeper. And so the negative version getting steeper looks like this, right? It's not the best drawing, but you get the gist. And what I'm trying to point out is, notice how the function is closer to the y-axis on both pieces. Don't be tempted to stretch it out outside of that red line. It's got to go steeper. And so if it's steeper, that means it's closer to the y-axis. Whereas if we multiplied by something less than 1, it would kind of do the opposite. It would be out here for the negative values, and then it would be over here for the positive ones. Right? This is what maybe 1/5 x to the fifth might look like. And so it shrunk down, which made it look wider, but it's a vertical stretch. And I want to compare this to the next page too, because the next page we're going to do horizontal stretching, and this looks a lot like a horizontal stretch to me too. And so you got to be a little bit careful about the slight distinction between the two of them. Let's combine one, though, if there aren't any questions about this. Let's do a combination one. That's really what we want to work towards, is doing multiple transformations in one, right? Questions before we look at one? So let's do this one. Let's do minus 1/2 x squared plus 1. And so I'm going to write down the details of what's going on here, and I don't think there's going to be enough room to write another one. So just be aware that you can write on this part of the page, and we're not going to draw another graph on this page. So there's 3 things going on here. First of all, we need to know what we're transforming, right? Like, what's the base function is what we call that. Which one of these functions on this page are we transforming in this particular problem?
X squared.
X squared, right? We've got an x squared, and it's got some things happening to it, but the point is that sort of the main takeaway is we're transforming x squared. Okay? And there's 3 things going on. We're multiplying by a negative number. It's a number that's less than 1, between 0 and 1, and we're adding something on the outside. And so that's a piece of like each of the last couple pages, right? So what's the minus sign do? That's going to be what kind of flip? Vertically or horizontally? Is it on the outside of the function, or is it multiplying the x inside of it? So this was on the previous page here, right? Which one of these 2 things is it? Is it on the outside or the inside? It's on the outside of it because it's not inside the square. If we had parentheses here and then there's a negative and it was both being squared, that would be inside it, but it's not. It's outside of the x squared. Right? The x squared is being multiplied by negative 1, so the minus sign is going to flip it vertically. Alright. So that's the minus sign. What's the 1/2 doing? That's from this page. We're multiplying by a number less than 1. So the 1/2 is going to shrink it. Shrink it vertically. And then what's the plus 1 do?
Move it up 1.
Move it up 1. That's from the first page, right? That's shifting it up 1. So I might actually draw the original over on this page, on this one, and then I'll draw the transformation on the other one. You can draw them both on this one if you want. Right, so that's what x squared looks like. And so we're going to take this graph on the left, we're going to flip it upside down, move it up 1, and shrink it vertically. And so when I do that, I think it looks something like this. So that's going to be my minus 1/2 x squared plus 1. It flipped upside down and moved up 1. And then it flipped over, then it shrunk by 1/2. But notice that I flipped it before I moved it. This is kind of what Disa was alluding to before. I flipped it, I thought about flipping it first, and then moved it up 1. If I moved it up 1 and then flipped it, the graph would be down here. Do you agree?
It looks like it got closer to the y-axis when you shrunk it.
Yeah, I was trying not to.
Okay.
It should probably look a little bit wider. And so maybe wider. Let's pretend that's what x squared looks like. It should look a little wider. But again, we're just sketching these things, right? I'm not gonna sort of jump down your throat if it doesn't look too wide. Yeah. Disa? Maybe let me look at it and evaluate that, and then we'll come back next time and see if we want to share that. Other questions before we write down the intercept so far? And again, I like drawing it first because now I know I'm looking for 2 x-intercepts, one positive and one negative, and one positive y-intercept, right? And so the x-intercept, you let y equal 0, and so we get 0 equals minus 1/2 x squared plus 1. And that's something we can solve. You can use a quadratic equation if you really want to solve that using that, but we don't really need to in this case. We could subtract the 1 and get minus 1/2 x squared. We can multiply by negative 2 and get 2 equals x squared. And that means that x equals plus or minus the square root of 2. And again, like drawing the graph is a good way to make sure that you remember to do plus or minus. If you draw the graph and then you only get one answer, you should think, well, I need 2 answers. And that might help you realize that when you take the square root, you get 2 answers, right? And so this is at minus square root of 2 and positive square root of 2. And then the y-intercept, you let x equal 0. And we get y equals 0 plus 1, which is 1. And so that's up at positive 1. Okay. Questions about that? All right, there's one other thing we want to look at, which is horizontal shrinking and stretching. It's very similar to the last page in looks sometimes. Sometimes a vertical or horizontal stretch can look very similar to each other, so just be aware of that. Again, I'm not like grading you on your artistic ability or anything. I just want to see that you get the idea. And so notice the difference between the last page and this page. It's very similar to kind of the other distinctions. So on the last page, this is the last page, we multiplied by a number outside the function. Right? And in all these examples, the number was clearly being multiplied outside the function. This one, we're multiplying by a number inside of the function. So the x itself, which is in the function, is being multiplied. And if that number, we get the same situation. If that number that's being multiplied is bigger than 1, then it's a shrink in the horizontal direction. And if the number is less than 1, it's a stretch in the horizontal direction. And so we can see again the two pictures here. If the number is bigger than 1, it's like we took our original graph, which was the blue line, and it shrunk horizontally. And if the number is bigger than 1, I mean between 0 and 1, like this one, we took the blue graph and we stretched it horizontally. And so that's a little counterintuitive too in some sense, right? You might think when you multiply by a number bigger than 1 that it should stretch. But when you multiply by a number bigger than 1, what happens is you're cramming twice as much information in the same amount of space. That's what makes it shrink. I'm going to say that again, but let's draw a picture before, that'll help us visualize that a little bit. I will just add a quick note here on the right here, which is that this is very similar to vertical stretching and shrinking, except one thing that you might want to notice. Except the height doesn't change. But the x-intercepts do. So keep that in mind. So we, just think about the visually on these two graphs. If we stretch or shrink them horizontally, the heights of them still stayed the same. It's just the x-intercepts is what really changed. You can just see that in these two pictures. The height has stayed the same in all these pictures. It's just that the intercepts ended up changing, right? They used to be here, and now it's here. Used to be here, and now it's here. And so we'll see that when we draw a couple of them too. I'm going to start with by just looking ahead to something in the trig section, which is the sine graph. So I know we're not talking about this yet, but it's really nice to see a horizontal shrink and a sine graph. So I'm going to draw sine of x on this page, on this graph, and then I'm going to draw sine of 2x on this one. So sine usually looks like this. It usually has a height of 1 and minus 1, and then it does this kind of thing. It crosses at 0, pi, and 2 pi. This is looking ahead to the trig section. And then it does the same thing in the negative direction too. It kind of goes this thing over here. Oops, that should come up to 1. And it also crosses at minus pi and minus 2 pi. And so I like drawing this one for the horizontal stretching and shrinking because there's a lot of x-intercepts. And so when we stretch or shrink it, we're either going to have more in the same amount of space or less. But what we'll see is that the height is not going to change. The height is going to stay the same at plus or minus 1. We're just going to either cram more stuff in there or we'll stretch it out. So which type is this, first of all? Sine of 2x, that is. It used to be sine of x, but now there's a 2 inside there instead. And so is it, which one of these situations up here is it? Is it going to be a shrink or a stretch? It's going to be a shrink because we're multiplying by a number bigger than 1, and it's inside the function. You see how it's inside the function? See how the 2 is inside the sine, right? If it was outside, if the 2 was out in front here, it'd be vertical. It'd be a vertical stretch. But because it's inside, that's what makes it horizontal. And think about what's going on here. When you plug x values in, it multiplies that number by 2. And so it takes whatever you wanted to plug in, it takes 2 times that much and plugs it in. And so it's really taking like twice as much information and cramming it into the same amount of space. So if you take twice as much information and cram it into the same amount of space, it's doing this thing. It's compressing it side to side. And so that's what makes it a shrink. And so we're going to have the same graph, except we're going to have twice as many intercepts, but we're still going to have the same heights of 1 and minus 1. All right, so you want to draw that same graph, except have twice as many bumps in it. So I'm going to do it like this. I'm going to have 1, 2. They should all have the same height if you can. And so instead of going through at 0 and 2 pi, we have twice as many, and so we have 1/2 pi, pi, 3/2 pi, and then this would be 2 pi. And so we have twice as much stuff going on, twice as many intercepts. Try to make sure your graph goes to plus or minus 1. I didn't do the best job of that. And the same thing happens on the left-hand side too. So we have like this situation. So this would be minus 1/2 pi, minus pi over 2, minus pi, minus 3 pi over 2, minus 2 pi. Questions? I'm not expecting you to, sine was one of the ones on the first page, so I'm not expecting you to necessarily know this one. What you'll see in the homework occasionally is they give you some random graph and they say, they'll say like, here's f of x on the left. What's f of 2x? And you just need to know that it's a horizontal shrink. And so you might see something like this. It may not call it sine, but it may give you a graph and ask you to do a very similar kind of thing. Alright, let's do one more where we combine some stuff here. So let's do another one where we combine some things and more of a problem that we might see in this section. So let's graph x squared minus 4. That's going to be our base graph. X squared minus 4 as a base graph looks like this. So we took x squared and we moved it down 4, right? Just to be clear. And so that's going to look like a U shape that's moved down 4. And so that's going to be something like this. And if we want to know the x-intercepts here, so first of all, the y-intercept's easy. It's just minus 4. It used to be at 0, 0, and then it moved down 4. So we don't really need to do any algebra for that. For the x-intercepts, I'm just going to solve for them real quick, just to give you some more stuff to look at when you do this your own. You get this. You get x equals plus or minus 2. And so we see we have plus or minus 2 as those intercepts. So I want to start with that graph and then transform that graph. So let's start with that one and do a few things to it. Just going to say something. What was it? I'm not sure. Anyway, what we're going to do is we're going to transform this one. And we're going to do 1/2 x squared minus 4. And then we'll do 2x squared minus 4. And we're going to draw both of those over there. So I'll just do this one again dotted on this one. This was our original graph. This is my x squared minus 4. And so we're doing two things to it. We're multiplying. So first of all, notice how this is inside the function. This is what makes it inside the function, because the 1/2 is multiplying the x, and it's inside of the x squared. Right? This is like an f. If this is our f of x on the left, if f of x is x squared minus 4, then 1/2 x squared minus 4 is f of 1/2 x. Right? It's like I took a 1/2 x and I put it into there. This is a composite type thing. And this would be an f of 2x, right? This would be f of 2x. Again, you can see how they're inside of the x squared. They are also being squared. That's what makes it horizontal and not vertical. And so the 1/2, the 1/2 is going to stretch it horizontally, and the 2 is going to shrink it horizontally. And so the 1/2 might look like this. It's going to be a wider version of that. It's going to have the same intercept of -4, except it's going to be wider. So that's what 1/2 x squared minus 4 might look like. And then the 2x squared minus 4 is going to be the same thing but shrunk. And so it's going to have the same y-intercept, except it's going to be inside there. And so notice the y-intercepts all stayed the same, right? That didn't change, but the x-intercept all did. And so these ones used to be at plus or minus 2. And where are they now? Let's see. So for the x-intercept on 1/2, we have 1/2 x squared minus 4 equals 0. That means 1/2 x squared equals 4. We take a square root, and we get that 1/2 x equals plus or minus 2. And then we multiply by 2, and we see that x equals plus or minus 4. And so our stretched out ones are at plus or minus 4 now. And that should make sense because we stretched it by a factor of 2. And so it used to be at 2, now it's at 4. It used to be at 2, now it's at 4, because we stretched it out by 2. Without doing the algebra, what's the other one then? If we shrunk it in by a factor of 2, and it used to be at -2 and plus 2, what is it now?
1.
It's at 1, right? We divided it by 2 instead of multiplying by 2. I'm just going to write it out just in case that doesn't make sense. But we should get plus or minus 1. So we'll get 2x squared equals 4. We get 2x equals plus or minus 2, so that means x equals plus or minus 1. And so we get plus or minus 1 on that as well, just like we thought. I do want to make one other point here. If there aren't questions about this, let me just pause and see if there's a question before I make a point here. So notice that this this horizontal shrink and stretch looks a lot like a vertical one. Like if you look at the last page, it looks very similar to this kind of thing that we did here. This is from the vertical stretching page. This thing looks almost exactly like this one, because we can phrase this as a vertical stretch. So let me just show you that real quick before we do our group quiz here. So notice this. You don't have to write this down necessarily if you don't want, but if we do 2x squared minus 4, and we simplify this, so let's distribute the square. This is the same thing as 4x squared minus 4. And so this is written as a horizontal stretch, actually as a shrink. And this is written as a vertical stretch. And so this horizontal shrink is the same thing as this vertical stretch. And so I'm just trying to point out that sometimes they can be the same. So this implies that sometimes vertical stretch is the same as a horizontal shrink, and vice versa. It just depends on how you look at it. Questions about any of this stuff? That concludes the sort of transformation section. You'll work on this stuff in the homework. Let me just remind you, when you're doing the homework, guys, there are multiple choice questions because I can't ask you to draw something on the computer. I'm going to ask you to draw it just like we've been doing these on quizzes and tests. It's going to be just like this. So when you're doing the homework problems, please be drawing some pictures. You're just going to be wasting your time otherwise. The point of homework is to practice this stuff. If you're just kind of looking and guessing and clicking multiple choice questions, you're not getting the practice. Like you're missing the point. The point's not to get 100 on the homework. The point is to practice on the homework so you can get 100 on the quizzes and the tests. That's what's really most important. So please draw some pictures. Draw some pictures. Okay. So if you go back and look at the symmetry section, you'll see that what I had said was symmetry with respect to the y-axis is the same thing as an even function. So this thing on the left here is the same as symmetry with respect to the y-axis. And on that page, what I had said was odd functions are the same thing as symmetry with respect to the origin. And you can see that in the definition here, right? This is the definition of what it means to be symmetric with respect to the y-axis. So we say a function is even if when you plug in a negative x, the function stays the same. Right? That's the definition of what y-axis symmetry is. And we say the function's odd if you plug in a negative x and everything switches around. That means that the function's the same as the origin. And so in some ways, the other way to write this is that minus f of minus x is the same as the function. This is how we thought about it in the symmetry section. We thought about when you plug in a negative y and a negative x, the function stays the same. And so that's rephrasing it in a different way, but it means the same thing. And so let's just look at a couple of them. And do you remember what was a general rule of thumb for these things? I wrote down something on that page that was like, usually even functions have blank, and usually odd functions have blank. Do you guys remember that at all? It's kind of in the word. Right? What do you think even functions usually have as powers? Generalize that. 2 is an even function, but because it's an even number, yeah. Sorry, x squared, I mean. So usually even functions have even powers. If there's powers at all, right? So like absolute value is an even function, but it doesn't have any powers, or has a power of 1. So it's not all the time, but usually even functions have even powers, and usually odd functions have odd powers. So be aware of that for the homework. But the way you test for it is what you do, what it says right in this box. If we want to see if a function's even, we plug in a negative x and see if it stays the same. Right? And then if we plug in a negative x and everything switches, that's what this one says, and that means it's an odd function. So for example, let's just do a quick, I'm going to draw two simple examples here. Let's say we have f of x equals x squared. What type of function is that? It's even. It's got a square. It's got an even power. And if we look at the graph, we already know what x squared looks like. X squared looks like this, right? And so we can just visually see that it has even properties because it's symmetric with respect to the y-axis. And moreover, we can use this property just to check, right? If we plug in a negative x, we get negative x squared. The negatives cancel out, and we just get x squared. And so you can see that the function stayed the same. This is the original function. So when I plugged in a negative x, the function didn't change. And this is implying it's an even function. And again, visually we can see it because it's symmetric with respect to the y-axis, but look at this. It doesn't matter whether we plug in an x or a negative x. Both of those two values have the same output. That's what that formula is telling us. Both of those things end up being the exact same height, showing us that it doesn't matter whether we plug in an x or a negative x, you get the same output. That's what this formula is telling us right here. Questions about that? So let's look at a real simple odd function then. What about f of x equals x to the fifth? All right, it's got odd powers. And so that's a good indication it's an odd function. If we look at what x to the fifth looks like, it looks like it's symmetric with respect to the origin. All right, that's what x to the fifth looks like. And we can test use the box at the top and just test it. If we plug in a negative x, we end up with the opposite of what we started with. And by opposite, I mean all the signs are switched. All right, we'll get a minus x to the fifth. And so this thing is the opposite of the original. Right, we started with x to the fifth, and we ended up with minus x to the fifth. And so this is an indication that it's odd. Right, and we can verify that visually. And let's say we plug in the same two x values, but positive and negative. So let's do a plus and a minus x. If we plug in the positive x, we end up with some y value. And if we plug in the negative x, we end up with the same y value, except it's negative. That's what that formula says. If we plug in a positive versus a negative x, the same number, right? You end up with the same y value, but one's positive and one's negative. That's what the formula is telling us. Questions about this before I just ask you to think about one? This makes sense, this idea. So, if you want to check, you just plug in a negative x and see whether or not the signs change. So I'm gonna write down one on the left side of the page here and ask you to think about one. So think about this one real quick. Oftentimes you can kind of just look at it and tell. Just imagine plugging in a negative x. So what about this one? It's kind of a combination. The ones we just tried were super simple. This one's slightly more complicated. What's going to happen when you plug a negative x in? Just take 30 seconds and just think about that. And think about whether or not the function stays the same. Do all the signs switch? Or something in between? Maybe some signs switched, but some signs stayed the same, right? So just to be clear, when you do that, you end up with this, right? Minus x to the seventh minus 3 times minus x squared. And sort of what's the takeaway here? What happens? Yeah, one of them changes. The first one, you raise a negative to an odd power and it stays negative. But then when you raise the negative to the even power in the other one, it becomes positive. And so what we see here is this negative sign changed, which implies odd, but this negative sign stayed the same. And so we had a little of both in that one. It didn't completely stay the same, it didn't completely switch all the signs, and so this is neither. It's neither even nor odd. And so in other words, that one just doesn't have symmetry with respect to anything. If we graph that one, it's not going to be symmetric. It's going to be all over the place.